Welcome back, everyone, to the Mathematical Summit in Paris. The next lecture is by a regular speaker from the Mathematical Summit in Paris, Antoine Chambert-Loir, who has given talks in all 3 editions of the school. He is in his office in the Université Cité right now, and he will give us a Blackboard talk on electrostatics and number theory. Please, Antoine, the floor is yours.
Okay, so thank you, PRG, for this introduction. I'm very pleased to be here, despite the fact that I don't see anybody of you. I don't know how many people are online or watching this today or together or tomorrow or after. So this is my first, the first talk I do in this way. Namely, there is a blackboard and chalk, and a good chalk, but and I'm just in front of my computer, which is screening this. And hopefully you can hear me and read what I write. If you don't, please shout out, and I'll try to adjust. So in the titles, there are two things that may be completely unrelated to you, namely electrostatics, which is about electricity and the electric potential of stuff. Yeah. So when you have capacity of condensators or stuff like that, and number theory. I don't remember exactly what I said. Something which is clearly related to numbers and integers. So there are a variety of talks I could discuss, but I will focus on something that had many implications in the last century, and a story that started 1893. So the general topic is you take a power series and so by series it means that it goes from 0 to infinity, and there are stuff which are coefficients an and some power t to the n. Okay, so it means that it's just something that we see formally. It could correspond to something that we know, like a Taylor series of a function, or it could be a polynomial, but if it's a polynomial, it's not interesting. And the question is, can we say if it is special in some sense? Can we recognize? And by special, here I mean today, but special means that I want it to be the Taylor extension of a rational function. So let me say it more concretely and give some examples. If you want some examples, you could take, for example, 1 divided by 1 over t, and you probably all know that it's 1 plus t plus t squared plus t 3, etc. And so this is an example of a power series. The coefficients are all 1, and I want. Well, then I know the formula, so I know that it is 1 divided by 1 minus t. But in general, is there some formula of the same kind? So of course there are other examples, but basically, if f is of the form p of t divided by q of t, and what you can do is you can expand this as put this series in simple terms. So you will have a sum of stuff that looks like that. So you would have some stuff in some sum of terms which are of the form 1 minus alpha j t, and with some coefficients beta j, and maybe some exponent there. And here it's a theory that we know because you can take this formula, 1 divided by 1 minus t, but I will put alpha t. And so this will be the sum of alpha n, or alpha n t to the n. And now I can differentiate this series various times. So if I take one derivation, I get alpha divided by 1 minus alpha squared. And here, I apply g divided by dt, and here I get sum of alpha n, n, t, n minus 1. And so you get another series, and maybe you delete the alpha here, it's 1, and here it's n minus 1. I hope you can read the rest. And so you get another series. Here you see all the coefficients are constant, and here you see an arithmetic progression times geometric progression, so a mixture of some stuff. And if I differentiate once more, I will get, I'll take a yellow chalk. I will get, for example, 2 alpha and divided by 1 minus alpha t squared, cube, sorry. And here I will get here n minus 2, and if I take out the alpha, it's n minus 2, and there is an n minus 1 that appears. So here now we get something which is exponential and times the polynomial stuff. And so there are formulas to compute this. And basically, it's just binomial coefficients. So something that should be alpha v to the n, and some binomial coefficient, which would be minus n, but that's okay, and t to the n, with strange versions of the binomial coefficients, but it's not really important. And so the question is how to recognize if f, at the starting point of the story, f is of the form sum of a and tn, and you want to see whether an here, write it in, whether this en here can have some expansion of this form with the form of beta gn, alpha gn with some coefficients. And in some sense, it's the answer is well known, and it's known for a long time. And maybe we could have said it at the very beginning of the talk. It said that f is from a and tn is the expansion of a rational function if and if the n satisfy a linear recurrence relation. And so for 1 divided by 1 minus t, we have n, which is sum of tn. We have n, which is always 1. And the relation is an plus 1 is an in some sense. But if you take 1 minus t squared, which is n t minus 1, what we get is n plus 1, and the relation is n plus 1 is n plus 1. You see, and if we differentiate once more, we will have something which is of degree 2, and here we will need a linear recurrence relation of length 2. The n plus 2 will be a combination of n plus 1, and constants. And in fact, what happens is that if it's a rational function f divided by g, for polynomials, then we get that the length, the length is, here the length is 1 and the degree is 1. The length is basically the degree of g. Okay, so the question is, in some sense, I've presented the question from an algebraic point of view very start of the talk, but the question you could say is you have coefficients an that come from wherever you want, and fields like combinatorics or number theory give a large supply of such families of numbers, and you want to decide whether there is some linear recurrence relation between them that would show that this sequence has some homogeneity. So this question was a very classical question in the 19th century, and too bad. And the starting point of the story I want to tell you goes back to 1893 and the French mathematician Émile Borel, which has been tremendously important not only for mathematics but also for the science with the social organization of mathematics. He was part in the creation of CNRS and stuff like that later on. So he has been, if I remember well, he has been Minister of Science in the government, etc. And so there is a paper by Émile Borel, which has a French title, Sur un théorème de Monsieur Hadamard, about the theorem of Mr. Hadamard. Hadamard was another very important mathematician of that time. You probably know him because he was one of the two people who proved the prime number theorem in 1999, sorry. So, but we'll see that this theorem of Hadamard it's much simpler, and we'll see what it is later. And so, in this paper by Émile Borel, Borel reminds you that there is a criterion using determinants. So we have a power series A and Tn, and determinants. Those are just numbers that we can compute using square matrices. And this criterion bears the name of maybe two German mathematicians of that time, either Hankel or Kronecker. And so what is this determinant? You just take this determinant. You start from some point. We start from not from the beginning of the sequence, let's say for some step n, and then we write an plus 1, and we go to an plus q. And the next line we write the same numbers, so they are exactly the numbers which are in the power series here, but we shift them a little bit. So n plus 1, n plus 2, n plus q plus 1. And if we go down and we want a square matrix, we have to go to a n plus q, and then it's a n plus q plus 1, blah, 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 a n plus 2q. Okay, and this is called the Hankel determinant. I will write it with G because letter for determinant. And we have two parameters, n and q. And let's say that we'll put q on the top and m on the bottom. Okay? And one case, Hankel is that, and Kronecker is just a case where n is 0. It's called the Kronecker determinant. And in fact, there is a criterion using those determinants that tells you when the power series is a rational function or not. That tells you whether the numbers a and satisfy a linear recurrence relation or not. And this criterion is basically that the determinants have to vanish a lot of time. So the equivalence, it's write it somewhere. I delay the names of uncodified, you can delete the name but not the role in history. And so the criterion is that f is a rational function if and only if there exists some q such that d and q is 0 for n large enough, and if and only if there exists some m such that dn, so sorry, not there is some m, let's rather say dq0 is 0 for q large enough. Okay. So what is the reason for this criterion? I won't prove it today because it's summer, it's hot, and maybe I don't know the whole steps of the proof. But in any case, there is something that we can say. If, and that explains why this term is true, at least in the in one direction. Assume that you have a linear recurrence relation. So assume that we have something like an plus q, and precisely q will be the length of the recurrence relation. So assume that n plus q is some coefficients c0 an, c0 an plus c1 an plus 1 plus blah 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 plus c q minus 1 an plus q minus 1. Assume that you get this, and you assume that this holds for all n, which is exactly the hypothesis that says that f is a rational function. Then what you can do in the last line is you can replace an plus q plus 1 by this formula. So what you get here for the last line, so here we get c0 an plus blah 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 plus c q minus 1 an plus q minus 1. Here you get c1 an, c0, sorry, an plus 1 plus etc. plus c q minus 1 and q, etc. And now what you can do is you see that this line is the sum of c0 times this line plus c1 times this line, blah, 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 blah. So this is exactly a linear combination of these lines, and the coefficients are exactly the coefficients c0, c1, cq minus 1. So just by the rules of determinants, you can subtract from this line c0 times that one, c1 times that one, etc. And now the last line becomes 0, 0, 0. And when you have a determinant such that one line is identically 0, then the determinant is 0. Okay? So at this point, you see that I've made a slight switch compared to the presentation of linear recurrence relation, because I want it here to be homogeneous. So there is no constant term, and at the beginning I pretend something like n plus 1 is an plus 1, which is not homogeneous, or even n. But then it's okay. I mean, you can just make a subtraction and say that n plus 2 will be n plus 1. It means that n plus 1 minus an is constant, and so you will get n plus 2 minus n plus 1 is n plus 1 minus an, and now you get a recurrence relation of length 1 more, but that's okay, and without any constant term. Just to provide and stuff. Okay, so I've shown one step of the proof, namely, or indicated how to prove one step of the proof. If f is a rational function, why are these determinants necessarily 0? And in the other direction, it's more complicated. But basically, you just take a minimal q so that either this or that holds. And then you manage to prove that you want that all that you get a linear recurrence relation. And for this, you just look at you do this by induction on the remaining integer, and you manage to look at the determinants seriously, and hopefully you can get it. Okay, so now thanks to this classical point of view of reducing linear recurrence relations or the expansion of rational functions to vanishing of some determinants, we are reduced to proving that. And the question is how to prove that determinants are zero. Do you have an idea? In principle, if you've studied a bit of linear algebra, then what you know is to prove that determinant is zero, you need to prove that there are that the lines or maybe the comments of your determinants satisfy some linear combination. I mean, for example, in the last not the last slide, but just a few minutes ago, the last line of the determinant was the linear combination of all the other lines, and that implied that the determinant is zero. But this is not the way you want to use, because precisely you want to prove that there is some linear recurrence relation. That's what you want to prove. So you don't want to use that way. And so the idea of Emile Borel is was both very simple and very surprising. Just prove an upper bound for them, and prove a lower bound. And say prove an upper bound. So how could proving an upper bound for determinant imply that it is zero? In general, no way. I mean, if your determinant is 10 to the minus 80, it would be very slow, but not zero. So there is one way, on the other hand, that makes a small determinant be zero if you will also assume something from number theory. And this is where number theory enters in. And the number theory condition that we assume is that all coefficients an are integers. Okay, so now we have departed from the standard algebra point of view that you have to prove some vanishing of determinants, but there is no way to do that. That would be non-tautological. So now we will do something. We first assume that those numbers are integers. Like in the first series at the beginning of the talk, 1 over 1 minus t, it was, and 1 over 1 minus t squared, it was just integers. And so we'll get this condition. And now, maybe you can guess where the upper bound, it's not bounds, bound. Where you get an upper bound, because if you assume that the an are integers, then the determinants here, it's the determinant of a matrix formed of integers, so there will be integers as well. And so the upper bound is just prove that j is smaller than 1, because j is integers. So if the absolute value of the integers is smaller than 1, then it must be 0. Okay? So this is a very basic. This is a very basic idea, but it is prevalent in number theory. All important theorems, maybe not all, many important theorems of number theory, of transcendental number theories, or about numbers, at one point use that if you have an integer which is smaller than 1, it is 0. Or in the other way around, if you have an integer which is non-zero, then it is at least 1. So now you know what you want to do and how you do that. So we have to use the theorem of Monsieur Hadamard. So now is the theorem of Jacques Hadamard. And the theorem is a very geometric way. It says that you know what if you have a determinant, and I have vectors v1, vn, and this determinant is the volume wrong here. You see the determinant is just the volume of the parallel pipette v1, v2, and v3. So this is the volume. But the picture is totally wrong because it's the picture is incorrect because you see I've drawn a picture where the parallel pipette is very straight. So in that case, it's like for the area of a rectangle or the volume of a cube, it's just the product of the length. But in general, this is not the formula. In general, your triangle could be very. This is a. It's hard to do a picture in 3D. So let's just show a picture of a triangle. V1, V2, and now you know that the volume of V1, the volume of this, it's not the volume of. It's not the product of the two lengths. It's just the product. It's V2 times the height of the parallel pipette. And what the formula that is nevertheless true is that the height here is smaller than V1, and so the volume is smaller than the norm of V1 times the norm of Vs. And here is the norm in Euclidean geometry. So this is a very important inequality, that the volume of the parallel pipette is smaller than the area of the length of the product of the length of the edges. And this is the theorem of Mr. Hadamard. Okay. So now we have to go further. We know that we will try to bounce the determinant using the fact that the product of the sizes of the cones are small. But remember what kind of determinant we are looking at. It's just the determinant where the coefficients are the integers that appear in the rational function here. So there is absolutely no way of showing that this side, as the product of those sizes, are small, except in one case where all coefficients are 0 in one cone, because here we have norms of vectors with integer coordinates, so the size is at least 1 in any case. So no hope to use this inequality just plainly on the Hankel determinant. So I will just write the hypothesis here. So the first hypothesis is that n is are integers, and there is a second hypothesis that that Borel does, is that assuming that f, at this moment we are using that I'm talking not only from sequences of integers satisfying OS, not eventually satisfying linear recurrence relations. But I want to talk about really something that looks like a function. And now I will start doing function theory and assume that f, this f, defines, in some sense, a function on a disk of some with center 0 and radius r, and the radius has to be at least 1, strictly greater than 1. So these are the hypotheses of Emile Borel, and the conclusion. Then f is working. And I want to tell you a bit about this story. So I can't see you, and I don't know. I can't watch. I can't look at your eyes or anything. So is everything okay for everybody? It's a good time to ask questions if you want. I know that 56 persons are online.
There are no questions yet, but everyone can see and hear you very well.
So don't hesitate. Yes, I could. There is something at the chat, but no questions. So don't hesitate to ask questions. You can interrupt me. I'm here for that. Okay, so I want to spend some time to explain you what define a function means, because it's really not clear and it's complicated. It's complex function theory. But I want to go back to the initial examples. So remember the initial examples, we have sum of Tn. Okay, and sum of Tn satisfies the fact that the coefficients are integers, clearly. And this An is always 1, so it's integer. And what about this as a function? Well, you know that if z is strictly smaller than 1, then you can compute f of z, which is 1 divided by 1 minus z. And z here it will be a complex number. And this is a function. But you know also that this formula doesn't really make sense for the greater than 1, because this series does not converge. It's sum of 1s, it could be plus infinity. And if you try to guess what the value at -1 is, you will get something which is complicated to define. And I said that it's reasonable to say that it's 1/2, 1/2. But in any case, we have this function here. We have the disk of radius 1. And here, in the interior of the disk, there is this formula. But you see that this expression, 1 divided by 1 over z, makes sense on the whole plane minus just the point 1. At 1, it's complicated. I have a ball, but if I could delete the ball, there is something. But in some sense, you see that this series defines a function not only on some big disk of radius greater than 1, but on the whole plane. And the only problem is some number. Here it's z equals 1, where there is a pole which I cannot get. Okay, and here this function, it's really a reasonable function in all sense. Here it's a rational function. We see it on the nose, but if we forget about that, we see that except for some finite number of points, it's a continuous function of z, and in fact it's also differentiable as a function of z, and finite number and some poles. Okay, and so this kind of functions by define. It was an important thing in 19th century analysis. It means that it will be a holomorphic function, or maybe a meromorphic function. That's a very barbaric term. namely that it looks like a rational function, except that you have to have power series, converging power series everywhere. So we assume that. And in some sense, all of the cases that I could show you would be similar, because at the end, Borel tells you that the function is rational, so it's very hard to give you an example that satisfies this hypothesis, which is not explicitly a rational function. It can be, but I'll show you another example, a non-example maybe. That comes from combinatorics, and which are where the coefficients are n, an are the Catalan numbers, and Cn is something like 1 divided by n plus 1, and the binomial coefficient 2 and n, and maybe there is a switch in the coefficients, I forgot. And here, if you take sum of Cn Tn, in some sense, you get the something like 1 divided by square root of 1 minus 40. And maybe the formula is slightly wrong, but that's okay. If it's not that, it's a closely related formula. And now, what you see is that what you get is that if you take again the origin, the point 1, the point 1 is where I'm interested, because obviously I want to go to a disk. Okay. And here, but you see that there is something happening already at t is 1/4. So here there is something very close. 1/4. And it's very hard to make sense of this series, because you see here, I could, if t is smaller than 1/4, I can really define, make sense of some of Cn z to Zn. It will have a reasonable formula, but it's impossible to cross. In some sense, it's possible to have it so here, but it's really impossible to cross this red line, because the square root is not well defined for a complex number, and especially if we try to define the square root of a negative number, when you approach that number from the top, you will be tempted to give some value, and if you approach it from the bottom, you will get exactly the opposite value. So there is really a problem, and so you see that in some sense, the best domain I could get to define this function is not a disk, but because of this square root, it would be something that go to start from 1/4 and go straight to the way to infinity, and outside of this red line, it would be okay. And maybe later in the talk, certainly in the talk, I will explain how this half line starting at 1/4 is really too big to make this series rational. And in fact, you see that there is some square root in it. So it's not a rational function. So now it's already 40 minutes. So maybe I will just sketch what Borel does. It takes indeterminants. And with some size q, so the matrix is q plus 1, q plus 1, and it goes from n plus q, then it goes to n plus p, and then for the moment you don't see the difference, but here is p plus q, and here is p plus q plus 1, and at the end, an plus q, an plus 2q. And now what he does is not only looking at this determinant in this way because we've seen already that there's no way to bound it clearly, but we can use the fact that if you have this function on a disk, so here its radius is now R, and this function on this disk has a finite number of poles. I don't know where the poles are, but that's okay. And what you can look if you take a polynomial defining these poles, and consider maybe not that G, but G that F Q is already an integer. So it's D of T for denominator, and consider F of T, D of T. And this denominator, it will be something like 1 minus some pole to some exponents. And at the end, something like that. And it's so it will be something like 1 plus C1T plus blah 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 plus CQ plus CP. And now you can try to guess what F of T, D of T does. This is another characteristic, but the Bn's are combinations of the ANs, and the coefficients are the C1, CP. So in some sense, Bn, let me delete the statement now. Bn is something like An plus C1 An minus 1 plus C2 An minus 2 plus CP An minus 2. This is what the expansion is. And now you see you can use this as a kind of linear relation. So what we can do here is whenever we have something which is beyond P, we can maybe we can invert this formula. We have An, which is Bn plus this. So now here, this An plus P, I can use the relation and make a convenient subtraction of these lines. And here replace An plus P by Bn plus P. So I should have stopped here at minus 1 and here P plus 1 to be better. But now this An plus P becomes Bn plus P, and here it's Bn plus P plus Q. And here the same way, all of the lines I can get them from the lines above by combining. In fact, I have to start from the bottom and to go. And here, so the determinant, the and Q is equal to that. And so what happens is that I have the same integers as I had at the beginning, but at some point I get the B's, which are the coefficients of this series. And this series has a property that it defines a function without poles. Because I've cancelled all the poles I could have in this disk of radius R, or maybe in a slightly smaller disk, because there could be poles approaching the boundary of the disk. I have on a disk R minus something. And now 19th century complex analysis tells you that because of that, these numbers Bn have to decay very, very fast. I mean, we have seen for the first examples, which were 1 divided by 1 over T, that it was sum of Tn, the coefficients were always 1. And we have seen that there is a pole at T equals 1. But if I delete the pole, and if there is no pole on the disk, then in some sense the series has to converge at each point of the pole. And that tells me that Bn in some sense is smaller than R to some minus n, maybe by slightly decreasing R. So we get an upper bound like that. And so now we can do something. We can do also something that says that an, the coefficients an, they cannot be too big because the function, because there are no poles here in some very small disk, so there is a similar inequality of this form. And now here on this formula, we can use the Hadamard inequality on the lines, and so saying that the absolute value of the MQ is basically bounded by the size of this vector, but all the coefficients are something like r to the minus m. So in some sense, this is r to the minus m, and I have p coefficients which are basically of this size, and here I have q minus p and q plus 1 minus p coefficients, which are roughly of the size r to the minus m. And now what we do is we take the m, these exponents outside of this. It will be say 1 divided by rp r q plus 1 minus p, and divided to the power m. And now we win, because this number is the product of some fixed power of p. P is chosen, and then I have the choice for p and q. So now I can take q very big, and p just given by that. And now if q is very big, this number is greater than 1, and so it's 1 divided by growing power m of something which is bigger than 1, so it goes to 0. If r is if q is large enough when n goes to infinity. And using the first algebraic criterion, I conclude the proof of Borel. Okay, so now I've explained you a bit of number theory and a bit of algebra, and I really need to go back to the other word of the title, which is electrostatics. And the question of electrostatics came in 1921 with a Hungarian mathematician, Polya. Hope I made no mistake in the accents. But, so, and it's 1928, sorry. So the question is, can one replace, can one prove a similar theorem when the disk is replaced by something else? And what is the condition? How should one replace the condition that R is strictly greater than 1? And so the answer is you first need to do something strange. So what you will do is that you have your plane, you have your domain. Here there is 0 somewhere. Remember the case, the case where we have 0, 1/4, and the open set was just the complement of this half line. So here we have some domain omega, and you know that this is a complex plane. So in fact, the complex plane you can view it. It's infinite, but there is a way to view the complex plane on a sphere. So we will put the north pole, which is the point at infinity, in the plane, and here there is the origin, and the origin is there, and my domain is complicated to write, but if you draw, but it would be this way. And so I won't draw the interior of the domain, but rather the. So let's make a big domain. Like that, and on the other side, and I don't know what it is, like that. And so I will draw everything outside of the domain. So we draw U on the sphere, which is called the Riemann sphere, because Riemann understood how the sphere minus North Pole could be made as a complex plane using a projection. And now I make the exterior of U as some with metal. On some metal, and the important point of metal is that it conducts electricity. So I make the exterior of U as metal, and I put an electron at 0 or a proton, whatever. Okay. Okay. And now when you do that, what you can you put it in metal, and not only you put it metal, but you put it to the mass. So, yeah. And so it means that all outside, all the part which is in metal would be at the potential 0, at the electric potential 0, and you compute the potential. You compute the potential at this. So you measure the electric potential. What I'm saying. Yeah. There is something strange. Okay. Well, around 0. So not really at 0, because at 0 there is an electron or maybe a proton, or you want charged proton. So you cannot measure the potential at 0, because of the proton, the charge is, the potential is infinite. But what you know is that the potential, if you look close to 0, you know that it's of some form logarithmic of absolute value of z, and minus 1. Well, it's of this form. There is some number divided by something like this to 0. So this is the rough form. No, sorry. The rough form of the potential around 0. There is a pole, a kind of pole, a logarithmic pole around 0, but there is some coefficient, which I call C, and C is exactly the capacity. So the reason for which we have logs, maybe you know about Maxwell laws and what happens for electric potential in free space, and there is formulas are as for gravitation. It's some potential in 1 divided by the radius, the distance to the charge. But here it's electricity in dimension 2, and in dimension 2, what plays the role of 1 divided by r is it's log of 1 over r, or log of r, and it goes that way. I mean, in dimension 4, it's 1 over r squared, etc. And that's in dimension 2. If we add 1 over r to the 2 minus 2, it would be 0. That doesn't work. So there is a slight switch. It goes from polar potential of over 1 to logarithmic potential. So this is the formula. And here is something C of U. And the theorem of Polya is very clear now. So let's say one thing. If what does it mean to have CU big or CU small? If you have U inside of something bigger, then CU is smaller than CU. So when you grow, let me. Sorry. Yes, when you have it grow, then capacity. And the theorem of Fourier is that if CU is strictly greater than 1, then F is not. So now you see, I've said enough about this story to feel that, and also the conditions of the ANs is still there. So now I've said enough that you can guess that there is a relation between the fact that some sequences of integers satisfy a linear recurrence relation and electrostatics, namely the capacity of this set U, or in fact, it's not the capacity of U, it's the capacity of the complement static. From electrostatics, the condensator is made by the complement. But for this talk, I can write it as C. And what is the relation between the two theorems? Well, the theorem of Fourier is a generalization of the theorem of Borel, because when U is just a disk, okay, remember we need to have some function V, so I need to tell you a bit of what is V. V has to be a solution of the Laplace equation. The Laplacian of V is identically 0 on U, but you remove the origin. Well, we have put a singularity, and V is this way. And there is a way to define a function like this. I'm sorry, let me delete it. I need some space. So the potential is the solution of the Laplace equation. And on the disk, the potential is very easy to compute. It's just radius divided by log of radius divided by modulus of Z. So the fact that it works is that because it's very easy to prove that Laplacian of V is 0. At least it's not easy, but it's a standard fact in complex function theory. When Z goes to the boundary of U, absolute value of Z goes to R, and so this goes to 0 at the boundary. And so here we want that V is 0 on the boundary. And because of that, Fourier implies Borel. So I won't give you the proof of this result because okay, I've done enough proofs for today. But I want also to tell you what happens for the Catalan series. For the Catalan series, you remember we had that U was T deprived of the half line 1/4 to infinity. Okay. And then the point is that the capacity is exactly 1. See, it's exactly the example of the Catalan series. It's a case where the capacity is 1, and so we cannot prove anything. So because potential theory, so potential theory is a branch of function theory that studies this Laplace equation either on the plane or on the 3 space or in more general context. And because of we do not live in a two-dimensional world, but because of it can serve as a very as a simple model of electricity for the three-dimensional world. And at least it is also connected to complex dimension theory. So there have been a lot of computations of capacities in the plane. And these computations give two stuff. So in fact, you see we are in the plane, and here, so we have the point 0, and we have to remove 0 here, and to look at what the complement of U. So what is nicer to do is to do an inversion and to put the point to put the origin at infinity, and now the complement of U becomes a compact, closed bounded set. Okay, inside. Just doing inversion. So if we take, I do the picture again. If we take for U some disk, what we get by inversion is just so here's this, and now we get the compact set of compact disk of center 0 and radius 1 over r. And so maybe okay. And if we do the other example of the 0 and some half line here, what we get, what you do the inversion is just a segment going from 0 to 4. Okay. And so what potential theory teaches you is that the capacity of a disk is the radius, and the capacity of a segment is the length divided by 4. And there are many other computations that people can do, but those are the really very important definition that you can prove at the beginning of the study of theory. Okay. We'll switch pages, but I can't. Okay, but I want to tell you. I think that's about how electrostatics comes into the story. It also comes in a different flavor, which was introduced by another Hungarian mathematician, Cité, at the same time. So, who introduced the notion of transfinite diameter. But maybe yes, so the relation. Okay. So I will try to for the last half hour of the talk to tell you about applications of how these theorems could have applications. And in fact, I know of two applications. One was in 1960, and the other is in 1987. In 1960, there is the American mathematician Bernard work, proved the conjecture of André Weil. And in 1987, the mathematician Jean-Paul Bézivin and Philippe Robard could prove the theorem which is called the theorem of Lindemann-Weierstrass, which is a generalization of the transcendence of E and pi. So what I'm really trying to tell you now is that this stuff at the beginning of the talk, which was about power series, determinants, volumes which are smaller than products of the volumes of parallel pair pipettes which are smaller than products of length of edges, and electrostatics or capacity transonic dynamics, all of this has consequences to here transcendence of E and pi, and I'm pretty sure you have heard about this and how it's structured. Many questions in number theory and complex function theory up to its proof by Lindemann in 1882. Yeah, or maybe slightly later. And the other application is conjectures of André Weil, which are related to something quite complicated in algebraic geometry and solutions of Diophantine equations, other finite fields, really stuff which is complicated. And but a proof of that number of solutions or of some equations satisfy some linear recurrence relation, and which are embodied in the rationality of some person. There is one caveat, one thing you could pay attention to. It's not exactly those theorems that generalize very well. It's rather generalizations that involve not only complex function theory, but p-adix numbers. So for those applications, I won't say very much about the detail, but it's really that you have to look at this really strange world of p-adic numbers and put it into the picture and look at functions. I've said, remember in the statement of the theorem of Borel, define a function. Something had to define a function on some disk. Now the function has to define not only a function on some complex disk, but also a function on some p-adic disk. And in the case of Bézivin and Robard, many p-adic disks for many prime numbers p, in fact, infinite series of prime numbers. So really some new part of number theory that I won't tell about. But the conclusion, in any case, is that given that this series, which is assumed to have rational integer coefficients, something like that, and defines a function on many open subsets in many worlds, the complex worlds, the p-adic worlds for one p or many p's, depending. Then, if some condition, which is really a product of capacities or product of transonic diameters, is strictly greater than 1, as in Borel and Polya, then you could get rationality. Okay, so this stuff is too technical to be discussed here, but what I want you to remember is that it's a natural generalization and something that we. So it's too complicated to talk about dwarf because I cannot, don't have the time to explain you finite fields and stuff like that. But I want to say a bit about this work of Bézivin and Robard. And I'm thrilled to tell you that yesterday you had a lecture by Fritz Beukers, and one after Jean-Paul Bézivin and Philippe Robert published the new proof of the Lindemann-Weierstrass theorem, Fritz Beukers observed that in fact one can remove from the proof all the complicated history that I've told you regarding capacities and so on first, and all the complicated history that I'm going to tell you now. But in some sense, Beukers understood how one could take all these arguments together in this case and make a very simple proof of the Lindemann-Weierstrass theorem. I invite you very strongly to read that proof. It's been published in '87 as well in the journal American Mathematical Monthly. It's very easy to find. In the end, you get a very nice original proof of the transcendence of ENY, which can be read and studied at all age. Okay, so now the last sorry, my notes are last part is also governed by a question of Chambert-Loir, 1921, is take a power series F with integer coefficients and Poirier gives you one condition that makes this series rational. Assume f prime, the derivative, is a rational function. Then f is a rational function. And in fact, essentially, you could get that this theorem is true as a consequence. It's not really a consequence of the theorem of Borel, unless I'm making a mistake. But you see, we have a series with integer coefficients. We want to prove that it's a rational function. So what we need to prove, if we believe in the strength of Borel's theorem, is to prove that we can define some function f, that f defines a function on a big disk. And in fact, it defines the function on a big disk, because you can take the function f prime, and, you can take f prime, and maybe f prime folds. You don't know, but from this folds, in some sense, there are ways to understand that these folds are really folds for f, and that they don't matter too much. And so, in fact, so in some sense, what you take this function here, and you can show that antiderivative in some sense exists. And if you can prove that, you show that f defines a function on the big disk, maybe with folds, and you conclude using Borel. So this is not a proof, but rather an indication that the proof is possible. And that's what Bézivin and Robert proved or studied. And the first one to do this was Bézivin, is to generalize this to more general linear differential equations. So it means that I take a differential equations. Differential equations. It's really something that I take some LF, which is say Cn of t Fn plus C0 of t, and C0 Cn are rational functions. So this is the definition for LF, and assume that if LF is rational, then F is rational. Okay, and so these more general differential equations were coined by Bézivin, exactly Polya equations, Polya operators. Okay, L is a Polya operator if whenever F is a polar series with integer coefficients such that LF is a rational function, then F is itself a rational function. And there are conditions for this to hold. It's not so easy to be a Polya operator, but Bézivin and Robert could prove the following step. And they take a very simple operator of this form. It's for an operator of degree 1, so it says only one derivative. And what they prove is that if you take, in fact, we can also generalize not only to integer coefficients in this case. If F has rational coefficients, positive radius of convergence, and LF is rational, then F is rational. And what is incredible is that from this theorem, which you might find strange, and maybe you could really wonder why do people want to study this, you could get the theorem of independent class, and which is the following: you take complex numbers A1, AN, sorry, not complex numbers, which take algebraic numbers. By algebraic, I mean that they are all solutions of a polynomial equation with integer coefficients, and you assume that they are pairwise distinct. And I take B1, Bn, non-zero algebraic numbers. Then the complicated expression B1 exponential of A1 plus theta plus Bn exponential of An is non-zero. So this is in the number of Schraft. And how do you get? I promised you about transcendence of E and pi. Let's look at how you could prove that pi is transcendental. You just take the formula 1 plus exponential of I pi is 0. And so if pi were algebraic, then I pi would also be algebraic. And so you take A1 is 0, A2 is I pi, B1 and B2 are just 1 to contradict this. And for the transcendence of E, the other constant, then you take just you assume that you have coefficients B, say Cn and En plus if C0 is 0. If E is algebraic, it is solution of some equation of this kind, and with non-zero integers C0, C2, C1, C2, Cn, and so you contradict against this. So you see that this theorem is very general and implies many results in number theory, in transcendental number theories, in particular, a quick proof that phi and E are transcendent. So what is the relation of these two theorems? The take of Bézivin and Robin is that they are equivalent. So how can one prove the equivalence? So I will delete this white part. And so we will start from, we want to prove this, so we will argue by contradiction. We assume that it is 0, and we take for f the sum of dj exponential ajt. And so this is an expression which is sum over all n, and here is sum over all j, dj ajn divided by factor n. Okay, and for some reasons, in the hypothesis I've deleted, all this series was assumed to have rational coefficients, and here it's algebraic numbers. There is no reason for it just should be these numbers should be rational. But what you can do is, if you have a relation like that, you can take all the similar relations using the conjugates of the V's and the conjugates of the AIs. So it gives you other relations, and the sum is certainly not 0, or not necessarily 0. But you can take the product of this 0 relation and times all the other conjugate relations, and you get a series which is you will get, by expanding everything, a condition of this form, but with more numbers. And now, because you take all conjugates, you would have rationality properties, and those would be rational numbers. So I will assume that I get that. And the assumption is that f of 1 is 0. So f of 1 is exactly that. And so what Bézivin and Robin consider is just the function. If you have a function which is well defined, because you see it's a function of any value of z, and it vanishes at 1, then you can divide by z minus 1. And this is a reasonable function from the point of view of complex function theory. And so you consider it. And so what is the relation between G and F? It's hard to guess, but you see there is something on the blackboard that I've not used up to now, which is this operator L. And so the relation between L, F, and G appears via something which is called a Laplace transform, which consists in deleting the factorials which are at the denominator. So whenever we have a series phi, which is sum of Cn divided by factorial n Cn, associate with phi something which I will call, say, phi hat, which is sum of Cn Tn. And if we start from exponential of At, okay, which is sum of a to the n divided by factorial n t to the n, what you get is sum of an t to the n, which is exactly 1 divided by 1 minus at. And so if we do this for this, what you get for f hat is that f hat is the sum of bj divided by 1 minus aj. So f hat is a rational function. And now what you can also compute is that you have sorry, you can look now at g hat. Or at least the relation between g hat and f hat, which comes from this. And if you do that, what you prove is that sorry. Right, so g hat is exactly L of f. So you obtain g hat just by playing this stuff. No, sorry, it's the other way around. F hat is L of g. So you write f is g times z minus 1, and you perform this trick, and you get that L g hat is f hat. And now you apply that L is a Pauli operator. So, and this is where this stuff of electrostatics and periodic numbers come in. So L is a Pauli operator, G hat is a reasonable function, L G hat is rational because it's that. So G hat is rational. And now once G hat is rational, you look at what it is. And you look at how you get f hat from G hat just by applying this operator. And so consider an elementary pole of G hat. If G hat is a pole at somewhere, when you apply the derivative, d over dt, you get a pole of order 2 at least. And this, except 0 doesn't count here, so you do not remove the pole, and here you get no pole. And so the conclusion is that if G hat has a pole at some number, then f hat has a pole of order 1 more, so 2 or more at the same place. And here you look at f hat, there are only simple poles. So the contradictions are here is that contradicts the simple poles of f hat. There are other ways to conclude, but that's the simplest way. And so we have a contradiction. And when you have a contradiction at the end of a complicated theorem, you have to unwind all places where you have assumed something that might have been wrong. And the hypothesis that we've made is that the conclusion of the Lindemann-Weierstrass theorem did not hold, namely that the linear combination sum of bj exponential aj t j vanished. And so this must be wrong. And so this thing is non-zero, and the Lindemann-Weierstrass is proved using this combination of determinants, electrostatics, number theory, periodic numbers, and all that jazz. Okay, thank you very much for this.
Thank you, Antoine, for this lecture. So now comes a question session. I'd like to remind all participants that you can type in questions right now, and I will ask them to Antoine. Some of you have already done this. I will start by reading those, but maybe it might give some time to the other participants to type in some questions. Now, the first question from Leo is about one of the proofs. Oops, question has disappeared. 1 second. It's about one of the proofs that you were giving. It was related to a matrix that you were using to solve factorization of power series, and there was a matrix involved and you computed its determinant. The question is, could you say again how the determinant is helpful in the proof? What is the connection between the determinant and what you wanted to do?
I'm not sure I've understood the question because I'm not sure of what part of the talk the question was.
Perhaps Leo, you could remind me in the chat which proof you're talking about. So say again, sorry, Antoine.
What step of the proof? That's the question.
Yes, exactly. So Leo can perhaps give more information. What I understood, perhaps wrongly.
Try to produce the whole story, but maybe then.
It was when Emule was first introduced. That's Leo's answer.
What was introduced?
Emule. Emule. Are you sure, Leo?
So I try to say something, but I'm not sure I answered the question. So. But basically, if I want to summarize the initial proof, I had some series of EMTN. I have the condition that all the coefficients are integers, and F is rational by some criterion is that some determinants n plus q, n plus 2q, and plus q vanish.
Mm-hmm.
So it was for some q and m large enough.
Leo, is this what you're talking about?
Yeah, now, how do, so this is algebra, 19th century algebra. And how do I prove this? Is by showing, there are which is smaller than 1. Okay, and to show that they are smaller than 1, I use complex function series. I can't resist the fact that it is simple complex series. Complex series. So to do what? To delete the poles. So you remove the poles of F by considering G, which is the denominator times F of T, and G has some coefficient Dn, Pn. And now, by just the trick of determinants, essentially here you keep the A's up to some P minus 1, but all other stuff are replaced by the B's. And now what complex function series tells you is that the A's are not too large and the B's are very small.
Mm-hmm.
And now you apply Hadamard, but that tells you that, okay, this is not too large and this is very small, the determinant is small. And once it's small, it's smaller than 1.
Yes, very good. That was precisely the part that Leo was asking about, and he says thank you.
Broad overview of the proof in 1 minute.
Yes. Very good. Now there's another question. It's a reference request from Luisa. Where can one read about this, apart from revisiting your talk on YouTube?
So, it's complicated to give references. I mean, I presume that you do not read French, and maybe you do. So, of course, you can read the paper by Émile Borel. It's the complete works of Borel. The theorem of Polya and its version by its version also for periodic numbers. It's presented in a very influential book in French by Yves, for one of the rare French female mathematicians of the 60s. I mean, not too many female mathematicians. So Yves wrote a very influential book about periodic numbers, but she wrote it in French. So it's called Les Nombres Périodiques. And it's a notebook which I believe is no longer in print, but it's possible to get it on the website. I should not tell the name, but that's okay. You know them, and if you don't know them, you have to know them. In this book, there is a proof of the theorem of Polya and the generalizations due to Bertrand-Dias and work for periodic numbers. But unfortunately, there is no proof of the Lindemann-Weierstrass theorem in that book. And then you have the paper by Becker, Bézivin, and Robert, which is American Math Monthly, where you would have the naive proof. I mean, the proof which is stripped off everything like that. But nevertheless, I would advise to have a look at it. And from that paper, you can look at the references, and you get the initial paper by Bézivin and Robert, which is also in English in the journal Annals of Math, but it is slightly more complicated to read. But in any case, so you get this. And also, if you want to know about the relation between complex function theory and potential theory, electrostatics, and so on, there is a very nice book by Thomas Farnsworth, which is called Complex Function Theory. No, maybe it's not. Sorry, it's here in my library, which is just behind the screen. So I'm just trying to look at it, but I can't find it. Yes. So it's something like potential in the complex plane. Sorry. And this is a very nice book about potential theory, but also complex function theory. It tells you about all these holomorphic functions are. And it ends not with the, so you would say, you know everything about the capacities and so on, and you could read this part of Ilatamis, and otherwise it means that I have to write a book.
I think you'd find an audience for that.
Sorry?
I think you would find an audience for if you were to write such a book.
Okay.
So now a question from Kuidango. How can one deduce the existence of a pole of degree at least 2 of f hat from the rationality of g hat? So that was in the previous board, unfortunately.
But you want to, what do you want to do about the poles of degree at least 2? Do you want to?
So, so it was in the previous board, at least according to the question, you had 2 functions, f and g, f hat and g hat, in fact, and from the rationality of g hat, you deduced the pole of degree at least 2 of f hat. How did that happen? How did you deduce one from the other, is the question.
Because it's not there anymore, but there was f which was sum of bj exponential ajt, and g which was f of g divided by g minus 1. So maybe in the other way around, f is g minus 1 g. But on the point of view of the hat and g hat, what you get is f hat is n applied to g hat. And L is the operator which was T2 G over dt plus T minus 1. This is a poly, and that stuff is the main theorem in the proof in one sense. It is a poly operator. So once it is a poly operator, if you know that L G hat is rational, you know that G hat is rational.
Right.
Right.
Yes, yes, and you can find the poles from the expression. Very good, very clear. Thank you. Here's a more open question, probably. Are there applications to industry?
Oh.
You can choose whichever definition of industry that suits your purposes here.
Yeah, I mean, the academic industry doesn't count. It's not so clear. I mean, of course, maybe part of my talk had tremendous applications to industry in the 30s, 40s, 50s, 60s. At the time when you wanted to devise a wing, an airplane wing, and you wanted to understand, you wanted to make this plane as much aerodynamic as you could. So you had to understand how the flow of air would be outside of the wing. And so to understand that, sometimes it's complicated equations, but basically it's Laplace equation again. And so you have to understand the Laplace equation outside of the wing. So let's say that's the wing of it. And so it was complicated because people had really no computing resources. I mean, before the computer, there were planes before there were computers. Nowadays, you do numerical analysis on computers, and you have very good models, and you don't need this anymore. But at that time, there was a link between complex function theory and what is called conformal representation and the Laplace equation, and people could do more or less approximate conformal representations of the outside of your ring. And from that, they were reduced to much simpler forms to which they could apply techniques that understood. So at that time, to be a good engineer in the airplane industry, you needed to know complex function theory. At least you needed to know a lot of the conformal representations related to. But now those models are totally outdated. So.
There's no simulation, I guess, is the tool that is used.
Now it's probably better to do simulations.
I see. That's a fascinating answer. Thank you. This seems to be the end of the list of questions. And so perhaps this should be the end of the question session. Again, thank you very much, Antoine,
thank you
for this lecture.
Thank you for your attention here.